Okay guys, so the next thing we want to talk about is calorimetry. Now, calorimetry is an experiment that you use to measure the energy absorbed or released by an object. You can use it for food, you can use it for metal objects, any sort of object that you want to know how much energy it'll release. It's often used to identify unknown metals or to figure out the amount of calories in food items. One thing to make sure you remember is that energy is represented by Q, and if it's absorbed, your Q is a positive value, and it's a negative Q if energy is being released. And so when you do this experiment, there are two basic assumptions that you make, but what we're going to look at is how the experiment is set up before we talk about those assumptions. So the first kind of setup we call coffee cup calorimetry, and the reason why is because you use a styrofoam coffee cup when you do it. And the styrofoam coffee cup has some water in it, so I'll draw my blue water, and you measure the temperature of this water. So let's say that this red line, that's going to be our thermometer, okay? And our thermometer tells us that the water is 25 degrees Celsius, okay, which is about room temperature, so they probably got it out of the faucet. And what you also have is you have a beaker, and this water is usually pretty hot. It's normally been sitting on some sort of hot plate here, and it's got some temperature, and the hot plate is a particular temperature, and there's normally like a metal block in there or some sort of metal, and this metal, you can't really measure the temperature, but if you measure the temperature of the water, and let's say it's at 100 degrees Celsius, well, if that block sits in there for about 5 to 10 minutes, then the block will also be 100 degrees Celsius. And so what you do is, in order to measure the heat that's released by the block, you actually can only directly measure water. And so the first assumption that we make is that the Q of our water, so the amount of energy that's absorbed by the water, is equal to the energy released by our metal block. And so if the Q is negative, then that's what's being released, but we measure how much energy is absorbed. And so that means, though, that all energy released by the block or by the metal or the object or whatever it is absorbed by the water only. Now, this is important because when we move this metal block over into our styrofoam cup, okay, when you move it over, the block is going to be very hot and the water is much cooler, and so that means the water temperature is going to start to go up because it's absorbing the heat from the metal block. But we know that in the process of moving it, there was energy lost to the air, and the styrofoam cup is probably absorbing some of it, but in order to make the math work, we have to assume that the metal that is releasing energy is only absorbed by the water and not the cup or the air or anything else, okay? And the other assumption we make is you measure your initial temperature, and then you also measure the final temperature of the water, okay? So you measure your initial and final of the water, final temperatures. And so what you know, though, is that when you add the block to the water, the block is going to heat up the water, and eventually the water will reach a high number, and then it will start to cool down again. That very high number is your final temperature. And what we assume is that the final temperature of the water is equal to the final temperature of the metal block. Okay, so this means that T final of our water is equal to T final of our metal. Okay, now these two assumptions here that I'm highlighting in green are super important. You cannot do the calculations of this kind of experiment without them. Now, the other setup uses a ring stand, and this is for food. When you want to know how many calories are in for example, bag of Doritos, you look on the back of the label and it says that 5 Dorito chips are equal to 65 calories or something like that. Well, the way that they do that is by using a bomb calorimeter. Now, we don't have this type of equipment. You can look it up on Google to see pictures of it, but what we do instead is we do a pretty close approximation, and we use a ring stand. So this is the stand, and there's a little ring that hangs from it, or that's clamped to the side. And what we do is we use an aluminum soda can. So what you do is all aluminum soda cans have that little tab, and you use a stick or some sort of like a pencil or something, and you put it through the tab, and it hangs the aluminum can. It kind of dangles it from the ring. And what you do is you put your food source underneath. So let's say our food is this, and it's a Cheeto Puff. Okay, well, what you do is you put water in your aluminum can, just a little bit though, not a whole lot, just a little bit, and you light the puff on fire. And when you light the puff on fire, it means that the flames, which I'm going to draw in red, we'll do it in yellow. So the flames are going to start to go up into the can. And so the temperature of the water, so you'll have a thermometer again going through there. So the thermometer will be going through the hole in the can right here, and you'll measure the temperature, and the water is going to absorb the fire from the Cheeto that's literally flaming. It's on fire, and its temperature will change. So it's the same kind of idea here, where your Cheeto is going to release heat, right, when it's on fire, which means it's an exothermic process. But the water is going to absorb heat from the Cheeto, which means it's an endothermic process. And so the key thing to understand here is when that Cheeto is on fire, there's heat going into the air, into the aluminum can, but in order to make our math work, we have to say that the heat that's released from our Cheeto is the negative version of our Q of our water, basically saying that there's no other heat besides what was absorbed by the water, even though we know that there is. And so when we do a calculation for a calorimetry problem, this can get complicated, but the main thing that you have to do is organize your material. If you can stay organized, then actually solving for it is not that difficult. So the best way to organize it is first read your question. So it says, pellets of an unknown metal were heated to 95 degrees Celsius and then transferred to a calorimeter containing 175 grams of water at 20 degrees Celsius. The highest temperature recorded was 23.6 degrees Celsius, and there was a typo in your notes. It should say 96 grams of the metal were used. Calculate the specific heat capacity of the unknown metal. So, let's list out. We have information about a metal, and we have information about water. And it's going to be important to keep track of what numbers go with which substance. Now, the key thing about your question that allows you to know what formula to use is that here it says specific heat capacity. And it also mentions temperatures, which means the only formula we have that has both of those is Q equals mc delta T, where we know that delta T is our change in temperature, so the final temperature minus the initial temperature. And so we're going to use that formula, which means eventually we're going to need to know all of that information for the metal and for water. So let's look. Let's just write it down. Q, M, C, T initial, T final, delta T. I'm just going to write all of that down for both. Q, M, C, T initial, T final, and delta T. I know that I'm going to need all of those numbers for both of them by the end. So let's figure out which ones we have. It says pellets of an unknown metal were heated to 95 degrees Celsius. So for our metal, our initial temperature is 95.0 degrees Celsius. It says, and then it's transferred to a calorimeter containing 175 grams of water. Well, grams measures our mass, so the mass of our water is 175 grams. And it says it's at 20 degrees Celsius, so the initial temperature of my water is 20 degrees Celsius. It says the highest temperature recorded was 23.6 degrees Celsius, so that means the final temperature of my water was 23.6 degrees Celsius, and we know that one of our key assumptions is that the final temperature of my water has to be the final temperature of my metal as well. So they have to be the same. It says 96 grams of the metal were used. So that means the mass of my metal is 96.0 grams. Now, since we have both of our delta T's, or both of our temperatures, for each of our metal and our water, we can calculate. So it would be 23.6 degrees Celsius minus 20.0 degrees Celsius, which means my delta T is equal to 3.6 degrees Celsius for my water. But my delta T for my metal is 23.6 degrees Celsius minus 95.0 degrees Celsius, which is going to give us, 23.6 minus 95 is going to give us negative 71.4 degrees Celsius. And it's important to note that this is a negative number because the metal block is cooling down while the water is heating up. So one of your delta T's should be negative, the other should be positive. Now, as we observe our columns, our metal and our water column, we're missing Q and C for both of them. But the important thing to remember is that your specific heat of water, so C of water, is listed. This number is on your periodic table. It's on the back. That's a number that you just need to know, and we give it to you. C of water is 4.184 joules over grams degrees Celsius. And so now we can see, well, for water, I know everything except for one thing. So that would probably be the easiest thing to solve for first. So the first thing we do is we calculate the Q of water. Let's try to solve for water. So Q equals mc delta T, which means Q of my water is going to be equal to the mass of my water, which is 175 grams, times the specific heat of my water, which is 4.184 joules per grams degrees Celsius times my delta T, which was 3.6 degrees Celsius. And when we look at our units, we can look to see which ones are going to cancel out. We see that we have grams and Celsius are going to cancel out, and so we just multiply our answers together, or our numbers together, which means Q of water is going to be equal to 2,635.92 joules. Now, because we know that, our basic assumption that we talked about earlier, which I'm going to write in this highlighted section over here, is we said that Q of our water was equal to the negative Q of our metal. Okay, essentially meaning that they're opposites. So because Q of water is positive, what that tells us is that Q of our metal is equal to the negative 2,635.92 joules. And so we can plug that in our formula, or in our little thing over here, our column. So we can plug that in, and now the only thing that we do not have in our metal column is C, which C is the specific heat capacity, which is what they wanted to begin with. Now, some of you will like to continue to leave C in your question. Some of you might prefer to change it to X. So you can say C is equal to X if you like solving for X the way you do in math class. So now we can say, okay, now we're going to look at our metal. So Q is equal to MC delta T. We know that Q is negative 2,635.92 joules, and it's equal to our mass, which is 96.0 grams. We do not know C, so I'm going to put X, because that's what I don't know, and my delta T is negative 71.4 degrees Celsius. So in order to simplify the right side of the equation, you are going to multiply those 96 and negative 71.4, and you get negative 6,854.4 grams times degrees Celsius times X, which is equal to negative 2,635.92 joules. And to solve for X, you just divide by negative 6,854.4 grams degrees Celsius on both sides. Negative 6,854.4 grams degrees Celsius. That cancels out. So therefore X, which is our C, is equal to negative 2,635.92 divided by negative 6,854.4, which gives us 0.38 joules over, oops, sorry about that. Let's go back to our problem. Kind of slid over. Joules per grams degrees Celsius. And that's how you solve for that problem. In this next problem, I'm not going to go through the whole problem because I don't want this video to go over 20 minutes. One thing that I will say, though, is make sure you list out your metal versus water columns, okay? And make sure you notice here, if this is the mass of the cup plus the water, that means the mass of my water would be equal to 180.89 minus the 2.31 grams that comes from the empty cup, which would give you 180.89 minus 2.31 gives you 178.58 grams. So you could, in your metal and your water columns list the mass of my water is 178.58 grams. Okay, so you're going to have to do that for your metal as well, where you're subtracting the 180.89 grams to get 600 grams of your metal. So keep that in mind. What I will tell you is if you're doing some practice, your final answer should be C of your metal is equal to 0.50 joules per grams degrees Celsius. And if you've gotten that answer, then you know you've done it correctly.